So let's talk about temperature. We already talked about how atoms and molecules that compose matter are in motion constantly. Because they're in motion, they contain thermal energy. Thermal energy is actually related to kinetic energy because it is an energy of motion. The temperature of a substance is a measure of its thermal energy. It's a measure of the motion of the particles. The hotter an object is, the greater the random motion of the atoms and molecules that compose it, and the higher its temperature. Have you ever thought about what temperature is? And that's one of those things that you're like, oh, we experience temperature changes, and you say, oh, he has a fever, he has a temperature. Actually, everyone has a temperature. Even a dead person has a temperature. It's just not appropriate for sustaining life. But what is temperature? Well, temperature is a measure of thermal energy. The warmer something is, the faster its particles are moving. So to help you understand that, I think of barefoot people walking on the sand. And I usually teach in Reedley, so I talk about Reedley Beach. But you guys, have you heard of Reedley Beach? It sounds all fancy, right? Mm-hmm. There's a lot of sand. It's just on the Kings River. But, in the summer when it's really, really hot, people hang out there. So the sand, as you can imagine here in the valley in July, August, the dry sand gets really, really hot. You could probably burn your feet on that, right? Do people just stroll along barefoot on the hot sand? No. We say they hot-foot it, right? They're going to go ding, 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 through the hot sand to the cold water, right? What about, you say you go to Pismo? It's like always cold in Pismo, right? That's why we go to Pismo in the summer, to be cold. So there, cold, wet sand, you're walking barefoot. People are just strolling along, right? So cold is slow, hot is fast. Hot particles move quickly. Cold particles move slowly. It is important to remember that temperature is different than heat. Heat is energy. It has units of energy, and it is the transfer of thermal energy. Temperature is a measure of thermal energy, but heat is the transfer of thermal energy. And we're not going to get super hung up on this, but we just do need to tell you about it. Heat, which is thermal energy transfer, occurs due to a temperature difference. You put a piece of cold ice in a cup of warm water, and what happens? There is energy from the warm water that's transferred to the cold ice, and they both end up being at the same temperature. Heat is the energy that's transferred from the water to the ice. Temperature is just a measure of the thermal energy that an object has. So heat and temperature, closely related, but not at all the same thing. Again, chemistry overlaps with many other sciences, and this is an area where chemistry overlaps strongly with physics. So we use 3 different temperature scales. So the Fahrenheit scale is what we're most accustomed to. Water freezes at 32 degrees, boils at 212. Room temperature, approximately 72 degrees. Those are kind of ballpark numbers. Normal body temperature is 98.6 degrees Fahrenheit. And the weatherman announces the temperature in degrees Fahrenheit. That's what we're accustomed to. But it's not a metric unit. We use the Celsius scale. It is sometimes been called the centigrade scale, which is actually very descriptive, but we usually use the word Celsius. So Celsius scale, that has abbreviation, degrees C. And on the Celsius scale, water freezes at 0, and boils at 100. You see how this is more metric than 32 and 212? Fahrenheit is classic English temperature, English unit, just like random numbers. Like, could you have chosen stranger numbers? At least they're even, but Celsius scale, 0 is freezing of water, and 100 degrees is boiling of water. I'm pretty sure that they chose those as reference points because they are very easy to obtain. If you have ice and water mixed together, you've got 0 degrees Celsius. That does not require a lot of technology. If you have pure water boiling at sea level, you have 100 degrees Celsius. Does not require technology. Okay, you could do it with a fire. So you could make a thermometer and calibrate it without any fancy equipment or anything. So they took between freezing and boiling of water and said, let's divide that into 100 degrees, because 100 is a nice factor of 10. So on that scale, room temperature is about 22, body temperature would be about 37. And then we have the Kelvin scale. The abbreviation for Kelvin is not degrees Kelvin, because the unit is a Kelvin, it's not a degree. The Kelvin scale was created to avoid negative temperatures. And so what it does is it takes 0 Kelvin is the lowest possible temperature. We call that absolute 0. Now remember, all particles are moving, and the temperature is a measure of that thermal energy that they have. So when the temperature is 0, that means that the particles are not moving at all, right? That is a theoretical temperature. They've gotten really, really close to that, but no one has actually obtained 0 degrees, not 0 degrees, 0 Kelvin. But that's the temperature at which molecular motion stops. So let's look at a comparison. So here we've got 3 thermometers. Fahrenheit, we've got water boiling up here. Celsius, it boils at 100. And for Kelvin, it boils at 373.15. What they did with the Kelvin scale is they just offset the Celsius scale. So they said, well, what is the absolute theoretical lowest temperature? We'll make that 0. But still, it's 100 divisions between freezing and boiling. So the size of a Celsius degree and a Kelvin is the same. The size of the unit is the same, but where 0 is different. The Fahrenheit scale has 180 degrees between boiling and freezing. So on the Fahrenheit scale, which is what we're more familiar with, absolute 0 is minus 459.7 degrees Fahrenheit. That's crazy cold, isn't it? That's just really unbelievably cold. Well, we need to be able to convert between these temperature scales. So these are the formulas. The Kelvin Celsius conversion is very easy because we just add or subtract 273.15. That's how much the 0 is offset. So if we have the Celsius temperature and we need to find Kelvin, we just add 273.15 and we've got Kelvin. The conversion between Celsius and Fahrenheit is a little more complicated because the 0 is not in the same position and the degrees are not the same size. So we take the Fahrenheit temperature and we subtract 32 to take care of 0, the freezing point of water being at a different place, and then we divide by 1.8 to adjust the size of the degree. You can also convert from Celsius to Fahrenheit, but then you have to rearrange the equation. So let's do some examples. Convert 358 Kelvin to Celsius. Now, temperature conversions need to be done using equations. We can't use dimensional analysis. So we're going to go, we've got 358 Kelvin, and we're trying to get to Celsius. So we need an equation. Degrees Celsius, well actually let's start with the equation that was given. The equation given on the previous page was this. Okay, Celsius plus 273.15 equals Kelvin. Well, how do we rearrange this equation to solve for degrees Celsius? We're going to subtract 273.15 from both sides. So we end up with degrees Celsius equals Kelvin minus 273.15. So the temperature in Celsius equals 358 minus 273.15. 358 minus 273.15. So calculator tells us 84.85, and the unit would be degrees Celsius. What about significant figures? Well, here we're subtracting. So we look at where the uncertainty lies. Here it's in the ones place, here it's in the hundredths place. The first number has no decimal places, the second number has 2 decimal places. No decimal places is a smaller number of decimal places. Uncertainty in the ones place is larger uncertainty, and so we're going to round this to the ones place. So we're going to report that as 85 degrees. Any questions? Yes. That comes from the equation. This guy right here. Okay. So these are the 2 equations we're going to use to do temperature conversions. Sometimes you'll see this as just 273, which if you're measuring things just to the nearest degree, that's fine. But if you're measuring to the tenths of a degree, then we really should use the 273.15. So we did that one. Let's convert 139 degrees Celsius to Fahrenheit. Again, temperature conversion. Darn it. So there's what we're given, and here's what we're trying to find. We need an equation. The equation is that degrees Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8. We need to rearrange this equation. And you need to be careful when you do this, because algebra has specific rules and you can't just make up your own rules. And sometimes students want to put the numbers into the equation first and then rearrange it. I went with that one semester and it was a disaster. So if you can do that successfully, great, but I don't recommend it. I think it's much easier to rearrange an equation without throwing in a bunch of messy numbers. So we need to get degrees Fahrenheit by itself. We're trying to isolate degrees Fahrenheit. So we have to undo the things that are being done to it on that side of the equation. So it's divided by 1.8, so we need to multiply by 1.8. Then the 1.8s will cancel out on that side and go away. Well, if we do that to one side, we have to do it to the other side, because an equation is like a balancing act. It's like a teeter-totter. And if you want to stay level, you have to do the same thing to both sides. This one's a little messy because it's got the multiplication and subtraction in it, so let's rewrite it over here. So 1.8 times degrees Celsius is equal to degrees Fahrenheit minus 32. Well, we're trying to get degrees Fahrenheit by itself. It has 32 subtracted from it, so we're going to do the opposite. The opposite of subtracting is adding, plus 32. Because 32 minus 32 plus 32 is 0, and so those go away. If we add 32 to one side, we have to add 32 to the other side. So here's our equation then. Degrees Fahrenheit equals 1.8 times the temperature in degrees Celsius plus 32. Any questions about rearranging the equation? Then we can plug our number in. So we've got 1.8 times 139 plus 32. .8 times 139 plus 32. 288.2 degrees Fahrenheit. Because this is an algebra equation and not dimensional analysis, the units aren't going to cancel out or work out at all. Yes? I got 282 also, and I wrote 288. Thank you. I can fix that, thankfully. My trusty rusty eraser. There we go. Thank you for telling me. 282.2. Now, what about significant figures? There's some funny things that can happen with significant figures and temperatures because we've got adding, subtracting mixed with multiplying, dividing. A Fahrenheit degree and a Celsius degree, while not being the same size, are similar in size. A Celsius degree is, a Celsius degree is a little less than twice as big as a Fahrenheit degree. So it's not like they're off by a factor of 100 or something, or even a factor of 10. They are close to the same size. So I think the best way to approach significant figures for temperatures is to just look at the decimal place where the uncertainty is in your starting temperature and reproduce that in your final answer. So in our starting value, 139 had uncertainty in the ones place. It was measured to the nearest 1 degree Celsius. We don't want to fool ourselves into thinking that our uncertainty is going to change just based on changing the temperature scale, because the units are so close in size. So we can't really say, well, that's 282.2 degrees Fahrenheit, implying that now we know it to the nearest tenth of a degree. So we're going to round that off to have the same number of decimal places as the temperature we started with. So we're going to call that 282 Fahrenheit. And that just makes life simpler too, because otherwise you have to go and you have to look at where the uncertainty was and all kinds of other things. And this 1.8, by the way, is an exact number. There are exactly 180 degrees to 100 Celsius degrees. So that's an exact number. That's not going to limit. And the 32 is also exact. And so those aren't going to limit our answer to two significant figures or anything like that. Any questions? Convert negative 321 degrees Fahrenheit to kelvins. So there's our temperature that we're starting with, and we're trying to get to kelvins. So we need an equation, because this is temperature conversions. Is there an equation relating Fahrenheit and Kelvin? Nope. So what do we have to do? We have to go to Celsius first. So we have to take the Fahrenheit and convert to Celsius using an equation. And then we convert from Celsius to Kelvin, again, using an equation. But still, good idea to figure out where am I going with this so that you can refer back to it if you get confused. So degrees Celsius equals Fahrenheit minus 32 divided by 1.8. So that's nice. We don't have to rearrange that. We're just going to plug the number in. So minus 321 minus 32 over 1.8 equals. Be careful not to lose that negative sign. So 321 as a negative number minus 32. Now we've got subtracting in the numerator and dividing. We want to tell our calculators to finish the subtraction. Because if you watch your calculator, after you type in 32, if you press divide, the display doesn't change. It still says 32. That means it's only going to divide 32 by 1.8. And that's not what we want. So we're going to go negative 321 minus 32. We're going to press the equal sign. Force it to finish the subtraction, because we want that quantity divided by 1.8. If that doesn't make sense, then use parentheses. Personally, I don't like them, but use them if you need to. Divide by 1.8, and I'm getting a number minus 196.11 repeating. And that would be degrees Celsius. Did I do it right that time? If you did not get that number on your calculator, then you have a calculator communication problem. And it's a shame to lose points and lower your grade because you can't talk to your calculator, right? Understanding chemistry is supposed to be the hard part. So if you need help with your calculator, please ask me. Are we done with the problem? No. Now, I don't want to round that off yet. This is infinite number of ones. Those are just repeating. Now we're going to take that degrees Celsius and convert to Kelvin. And so we use this equation, Kelvin equals degrees Celsius plus 273.15. So we take this number, minus 196.111111, and we add 273.15. So Kelvin equals, I have that number in my calculator, I'm just going to press plus 273.15 equals, we get 77.038, and the 8's repeat, and the unit on that will be capital K. So how should I round that number? We look at the starting number, 321 degrees, uncertainty in the ones place, so we're going to round our answer here to the ones place, and we're going to say this is 77 Kelvin. Any questions?